Chemistry is a study of matter, what it's made of, how it behaves, and how it changes. It explores everything from why your stomach digests food to how soap removes oil. Now, within chemistry, we have two massive branches. We have organic chemistry and inorganic chemistry. So, organic chemistry is a study of carbon containing compounds, especially those that also include hydrogen and often oxygen, nitrogen, and sulfur. Why carbon? Because carbon can form four strong bonds, making it uniquely flexible. It can build chains, rings, and complex 3D structures, the foundation of life. So, examples of organic compounds include glucose, DNA, proteins, methane. Now, organic chemistry study in pharmaceuticals is important because it describes how drugs are designed. In biochemistry, because it tells us how the body functions. In petrochemicals, because it is behind fuels and plastics. And in food chemistry, because of the flavoring and preservatives, where organic chemistry is most dominant. Now, inorganic chemistry deals with everything else. That means we have metals, minerals, salts, acids and bases, water, gases like oxygen and carbon dioxide. Inorganic compounds usually don't have carbon-hydrogen bonds, and if they do, it is not in the complex way organic compounds do. So, example of inorganic compounds are sodium chloride, that's table salt, water, ammonia, sulfuric acid, iron oxide. So now let's talk about some applications of inorganic chemistry. It's applied in material science, in catalysts in industry, electrochemistry, environmental science, and so have you. So understanding the organic or inorganic chemistry differences helps us to design better drugs that interact with your body molecules, detect pollutants in water and air, understand diseases rooted in molecular defects, and create materials that are more suitable, sustainable, and efficient. For instance, cancer often starts with a mutation in an organic molecule, the DNA, but treating it might require inorganic agents like platinum based chemotherapy drugs. Or take nutrition, we have vitamins which are organic, but minerals like iron and calcium are inorganic. Both are vital, both are chemical. Now, inorganic chemistry and organic chemistry surrounds us. Our sugar, our oil, our butter are all organic compounds or organic substances, whilst our salt, our baking soda are all inorganic substances. Now, in medicine, we have paracetamol, antibiotics, which are all organic, and then we have antacids, which is magnesium hydroxide, being inorganic. Think of cisplatin, a platinum-based drug that destroys cancer cells, or the lithium used to treat bipolar disorder. In buildings, we have plastics, being organic polymers, and concrete, glass, steel, or inorganic compounds. Now, let's look at some organic compounds and their nomenclature. Alkanes. Alkanes are saturated hydrocarbons. The general formula for alkanes is CnH2n plus 2. An example is 2-methyl butane. Alkenes are unsaturated hydrocarbons with double bonds. A general formula is CnH2n. An example is butene. Alkynes. Alkynes are hydrocarbons with triple bonds. A general formula for alkynes is CnH2n minus 2. An example is propine. Alcohols. Now the functional group of alcohols is OH. An example is propan-1-ol. Esters. The functional group is COOR, where R is the alkyl group. An example is ethyl ethanoate. Carboxylic acids with a functional group COOH. Aldehydes has a functional group CHO, and an example ethanol. Then we have ketones. The functional group is CO, that's the carbonyl between two C carbon atoms. Then we have amines. The functional group is NH2. It's an alkane plus an amine. An example is ethanamine. Then let's look at some terms in organic chemistry. Isomerism. Isomers are compounds with the same molecular formula but different structural arrangements or spatial orientations. Isomerism is divided into two broad categories. We have structural isomerism and stereoisomerism. Under structural isomerism, we have chain isomerism with different carbon skeletons, example being butane. We have position isomerism, functional group isomerism, tautomerism. And under stereoisomerism, we have geometric isomerism, optical isomerism. Then we have diastereomers. Now hydrogenation. Hydrogenation is the addition of hydrogen, that's H2, across double or triple bonds in unsaturated compounds, typically in the presence of a metal catalyst. Now types of hydrogenation, we have catalytic hydrogenation, partial hydrogenation, anti-hydrogenation. Then we have halogenation. Halogenation is the introduction of halogens into an organic molecule. We have one where we have radical substitution, electrophilic addition, and in aromatic compounds we have electrophilic aromatic substitution. Benzene and aromaticity. Structure of benzene is C6H6. It's planar, cyclic, fully conjugated, delocalized pi system. Example, chlorobenzene. Polycyclic aromatic compounds. These are hydrocarbons with fused benzene rings. Example, naphthalene, anthracene, phenanthrene. Now we have chirality and chiral compounds. A compound is chiral if it is non-superimposable on its mirror image.